Hi, in this video we will talk about voltage sources. We'll first look at what an ideal voltage source is supposed to be doing and how a practical implementation of this differs from the ideal situation. And we'll look at some of the consequences of this practical differences in a real situation. So let's start. We have here an ideal voltage source to which we have connected an arbitrary load. Now the goal of an ideal voltage source will be to maintain its voltage V no matter what sort of load you connect to it. So no matter what this load is and what current it is drawing, the voltage seen by the load should be equal to the voltage supplied by the ideal voltage source. If you were to plot the voltage seen by the load and the current taken by the load, you would see that the VI transfer curve would look basically like a straight line. So essentially, no matter what the load current is, the voltage given by the source and the voltage seen by the load is always going to be a constant. You can arbitrarily increase the load current and an ideal voltage source will still be able to maintain its voltage at the value of V, which it is set for. But a practical voltage source has some differences compared to this ideal situation. So one significant difference is that a practical voltage source will have its own intrinsic series resistance. So I'm showing this series resistance here. Now what would be the effect of this? Basically, the current that the load is drawing will have to flow through this series resistance. So through Ohm's law, you can expect that the current will drop a voltage across this resistance equal to I into Rs. So now the voltage seen by the load will actually not be V, which is what the voltage source is set for. It will be V minus I into Rs. What this does is that it makes the voltage supplied by the practical voltage source a function of the load current. It's no more going to be constant for any value of current that you are taking from it. Rather, you will see that the VI transfer curve will look something like this. As you keep increasing your current, the drop I into Rs keeps increasing, and so the voltage supplied by the whole practical voltage source actually keeps dropping. And the slope of this line, of course, depends on the value of the series resistance. If the series resistance is larger, it will drop down faster. If it is small, then you would see a slower reduction in voltage as you increase the current. Another issue with many practical implementations of voltage sources is that they have a limit on how much current they can actually supply. You cannot draw an arbitrarily large current from these kind of sources. For example, if you consider a regulator, basically a switch mode power supply, which is often used in laptops and PCs to power your motherboard, that beyond a certain amount of current drawn from it, the voltage will actually just collapse down to zero. So there's a maximum limit on how much current some of these voltage sources can actually supply. Other voltage sources like batteries and capacitors don't have this sort of a profile where it just collapses after certain current. In these cases, you can keep drawing larger and larger currents and the voltage will keep dropping, and eventually at some point it will just catch fire and burn up and the battery or capacitor will just get damaged. So you would want to avoid such a situation from happening if you were to use a battery or a capacitor as a voltage source. So that's one thing to keep in mind. Let's take a look at a voltage source used in a real life application. Let's consider the case where a lithium-ion battery is used as a voltage supply in your smartphone, for example. In this figure, I'm showing you a lithium-ion battery pack, which is providing a voltage supply to all the smartphone side circuitry. Now, a lithium-ion battery is at about 4.2 volts when it is completely charged, and it's at about 2.4 volts when it's completely discharged. It is not good for the battery to take it to this deep discharge condition of 2.4 volt. So what is often done is there's a monitor circuitry within your smartphone which checks to see the battery voltage being given, and when it drops below about 2.7 volts, for example, it just turns off your load. That way you don't take any more current from the battery and you stop discharging it. So let's say you've been using your phone for some time, and the battery has come down to about 3 volt. And let's say your smartphone circuitry is taking a current of 1 ampere. Now the battery has its own intrinsic series resistance. For a decent battery, a decent lithium-ion battery, this should be under about 0.1 ohms. Now, although your battery is at 3 volts, because there's a current flowing through the series resistance, there is a drop across this, and the voltage which is actually delivered from the battery and seen by the smartphone circuitry will be 2.9 volt, because 0.1 volt drops across this series resistance. Now, as you keep using your battery and you discharge it down to 2.8 volt, this will be at 2.7 volts. And so your monitor circuitry thinks that your battery is discharged and it just turns off the load, even though your battery voltage was at 2.8 volt. Now, this is not too bad. Okay, you're turning it off at 2.8 volt, but that's not too bad. Now, what would happen as your battery ages? Typically, as a battery gets older, the series resistance will increase by quite a significant amount. Let's say it increases to 0.5 ohms after a few years of use. Now, in this case, even if your battery voltage has come down to only 3.2 volt, because you have such a high series resistance, you will drop 0.5 volt across this when you try to draw a current of 1 ampere, when the phone tries to draw a current of 1 ampere. So the voltage delivered to the smartphone circuitry will only be 2.7 volts. So the monitor circuitry thinks that the battery is discharged and it will turn off the load, even though it was discharged only down to 3.2 volt. So this is actually the reason why your phone runtime drastically reduces as the battery ages. So even though your battery has been discharged only down to 3.2 volt and it potentially still had some charge capacity left in it, because of this increase in the series resistance, you will not get to use it. The phone will just turn off. So this is how over the years you will see a reduction in the total runtime you get from your battery, because as it ages, the intrinsic resistance of the source increases, and so the voltage actually delivered by the battery continuously reduces for a given amount of current. An even more annoying situation can be that, let's say you are using your phone for some power intensive application, like let's say you're watching a YouTube video. The current drawn by the phone would increase quite a bit. Let's say it increases to 2 amps. Now if we are drawing 2 amps through a 0.5 ohm intrinsic impedance, you're going to drop 1 volt across this directly. So even if the battery voltage is pretty high at 3.7 volts, that is the internal battery chemistry voltage is 3.7 volt, the actual voltage delivered by the battery will be only 2.7. And the phone will turn off when you try to use YouTube, for example, because of this huge drop you're seeing across its series resistance. So yeah, this was just to give you an idea of a practical consequence of what an increased series resistance means for a voltage source. Alright, so I hope you found this video useful, and in a future video we'll look at current sources as well.